A configuration of a transformer with a 480 volts, 3-phase, 3-wire primary and a 480 volts, 3-phase, 4-wire secondary offers several advantages. The primary reason is voltage regulation. The 480 volt secondary provides a more regulated voltage to the motors, which ensures stable operation. The 3-wire primary reduces voltage drop due to line impedance, making the system more efficient. Secondly, consider motor starting. During motor starting, high inrush currents can cause voltage dips. The 3-phase, 4-wire secondary provides a neutral path for these currents, reducing voltage fluctuations and improving motor starting performance. Thirdly, ground fault detection. The 4-wire secondary allows for ground fault protection schemes to be implemented. If a ground fault occurs, the neutral current will increase, triggering a protective device to isolate the faulty circuit. Fourthly, there is reduced cable cost. The 3-wire primary requires one less conductor than a 4-wire primary, saving on cable costs. The neutral conductor in the secondary is typically sized smaller than the phase conductors, further reducing cable costs. Fifthly, simplicity. The 3-wire primary is simpler to install and maintain than a 4-wire primary. The 4-wire secondary provides a convenient neutral connection point for ground fault protection and other devices. While the neutral is not used for power delivery to the motors, it still plays an important role in the system's safety and performance. To elaborate further, the use of a 4-wire secondary, even when the neutral isn't directly used for powering the motors, allows for a more robust and safer electrical system. The presence of the neutral enables the implementation of ground fault detection, which is critical for preventing electrical hazards and equipment damage. In the event of a ground fault, where a phase conductor comes into contact with a grounded surface, the current will flow through the neutral conductor back to the source. This increase in neutral current is detected by ground fault protection devices such as ground fault circuit interrupters or ground fault relays, which then trip the circuit breaker, isolating the faulty circuit and preventing further damage or injury. Without the neutral connection, detecting ground faults becomes more challenging and may require more complex and expensive protection schemes. The 4-wire secondary also provides a stable reference point for voltage measurements. This is particularly important in industrial settings where voltage fluctuations can disrupt motor operation and damage sensitive electronic equipment. A stable neutral point helps to maintain a balanced voltage supply, ensuring that the motors receive the correct voltage and operate efficiently. Furthermore, the neutral conductor can act as a return path for unbalanced loads. While the motors themselves may be balanced 3-phase loads, other equipment connected to the same electrical system, such as lighting or control circuits, may create unbalanced currents. The neutral conductor provides a path for these unbalanced currents to flow back to the source, preventing voltage imbalances and ensuring stable operation of all equipment. The smaller size of the neutral conductor in the secondary, compared to the phase conductors, is possible because it typically carries only the imbalanced current and the ground fault current, not the full load current of the motors. This reduces the overall cable cost without compromising the safety or performance of the system. The choice of a 3-wire primary configuration is often driven by cost considerations and simplicity of installation. By eliminating one conductor, the cable cost is reduced, and the installation process is simplified. However, it's important to ensure that the primary side is properly grounded to provide a safe and reliable electrical system. In summary, the combination of a 3-wire primary and a 4-wire secondary in a 480 volts, 3-phase transformer offers a balance of cost-effectiveness, simplicity, and safety. A 4-wire secondary provides essential features such as ground fault protection, voltage stabilization, and a return path for unbalanced currents, while the 3-wire primary reduces cable costs and simplifies installation. This configuration is particularly well suited for industrial applications where reliable and safe power supply is critical for motor operation and overall system performance. The ground fault protection afforded by the 4-wire secondary is not merely a safety feature, but also a critical component to maintaining operational uptime. Undetected ground faults can lead to equipment damage, fires, and even explosions, resulting in costly downtime and repairs. By quickly detecting and isolating ground faults, the 4-wire secondary helps to prevent these catastrophic events and ensures that the motors and other equipment continue to operate reliably. Moreover, the stable voltage provided by the 4-wire secondary contributes to improved motor performance and efficiency. Voltage fluctuations can cause motors to overheat, lose torque, and even stall, leading to reduced productivity and increased energy consumption. By maintaining a stable voltage supply, the 4-wire secondary helps to optimize motor performance and minimize energy waste. In addition to these benefits, the 4-wire secondary also provides flexibility for future expansion and modifications to the electrical system. The neutral conductor can be used to supply single-phase loads such as lighting or control circuits without requiring a separate transformer. This simplifies the design and installation of new equipment and reduces the overall cost of the electrical system. When selecting a transformer for a 480 volts 3-phase motor application, it's important to carefully consider the specific requirements of the system and choose a transformer with the appropriate kVA rating, impedance, and other characteristics. The transformer should also be installed and maintained in accordance with all applicable codes and standards to ensure safe and reliable operation. Regular inspections and testing should be performed to identify any potential problems such as loose connections, damaged insulation, or overheating, and to take corrective action before they lead to more serious issues. In conclusion, the 480 volts 3-phase transformer with a 3-wire primary and a 4-wire secondary is a versatile and reliable solution for powering motors in industrial applications. Its advantages in terms of voltage regulation, motor starting, ground fault protection, cost effectiveness, and simplicity make it a popular choice for a wide range of applications. By understanding the reasons behind this configuration and following proper installation and maintenance practices, you can ensure that your electrical system operates safely and efficiently for many years to come. The presence of the neutral wire in the 480 volts 3-phase 4-wire secondary system allows for the implementation of various monitoring and diagnostic tools. These tools can be used to detect and analyze power quality issues such as harmonics, voltage imbalances, and transient voltages, which can negatively impact motor performance and efficiency. By identifying and addressing these issues, you can improve the overall reliability and efficiency of your electrical system. Harmonics are sinusoidal waveforms that are integer multiples of the fundamental frequency of the power supply, which is typically 60 Hz in the United States. They can be generated by nonlinear loads such as variable frequency drives, electronic ballasts, and uninterruptible power supplies. Harmonics can cause a variety of problems, including overheating of transformers and conductors, increased energy consumption, and malfunction of sensitive electronic equipment. The neutral conductor in a 4-wire system can carry harmonic currents, particularly the third harmonic and its multiples, which can overload the neutral conductor and cause it to overheat. Voltage imbalances occur when the voltages and the 3 phases of a 3-phase system are not equal. This can be caused by unbalanced loads, such as single-phase loads connected to a 3-phase system, or by impedance imbalances in the power distribution network. Voltage imbalances can cause motors to overheat, lose torque, and even stall, leading to reduced productivity and increased energy consumption. Transient voltages are short-duration, high-voltage spikes that can occur on the power system due to lightning strikes, switching operations, or other disturbances. Transient voltages can damage sensitive electronic equipment and cause insulation breakdown in motors and transformers. A neutral conductor in a 4-wire system can provide a path for transient voltages to ground, reducing the risk of damage to equipment. By monitoring the neutral current and voltage, you can detect the presence of harmonics, voltage imbalances, and transient voltages and take corrective action to mitigate their effects. This can involve installing harmonic filters, balancing loads, or improving grounding practices. The neutral conductor also plays a crucial role in surge protection. Surge protective devices, or SPDs, are designed to protect electrical equipment from transient voltages caused by lightning strikes or other events. SPD are typically connected between the phase conductors and ground, and they divert surge current to ground, preventing it from reaching the protected equipment. In a 4-wire system, the neutral conductor provides a low impedance path to ground, which helps to improve the effectiveness of SPD. The neutral conductor also provides the reference point for the SPD clamping voltage, which is the voltage at which the SPD begins to divert surge current. A stable neutral voltage ensures that the SPD operates correctly and provides reliable protection against transient voltages. Furthermore, the 4-wire secondary configuration simplifies the process of testing and troubleshooting the electrical system. The neutral conductor provides a convenient point for measuring voltage and current, and it can be used to isolate faults and identify problems. For example, if a ground fault is suspected, the neutral current can be measured to determine the location and severity of the fault. The neutral conductor can also be used to test the effectiveness of ground fault protection devices and to verify that they are operating correctly. In addition to these technical considerations, the choice of a 4-wire secondary configuration may also be influenced by regulatory requirements and industry standards. Many electrical codes and standards require the use of a neutral conductor in certain types of electrical systems, particularly those that serve sensitive electronic equipment or require ground fault protection. These requirements are designed to ensure the safety and reliability of electrical systems and to protect people and property from electrical hazards. When designing and installing a 4-wire secondary system, it's important to comply with all applicable codes and standards and to follow best practices for grounding and bonding. Proper grounding and bonding are essential for preventing electrical shock hazards and for ensuring the effective operation of ground fault protection devices. In summary, the 480 volts 3-phase transformer with a 3-wire primary and a 4-wire secondary is a well-established and widely used configuration that offers a number of advantages in terms of safety, reliability, and performance. The neutral conductor in the 4-wire secondary provides essential features such as ground fault protection, voltage stabilization, harmonic mitigation, surge protection, and simplified testing and troubleshooting. While the neutral may not be directly used for powering motors, it plays a critical role in ensuring the safe and efficient operation of the electrical system. Therefore, it's important to carefully consider the benefits of a 4-wire secondary configuration when designing and installing electrical systems for industrial applications. Also, in addition to the previously mentioned points, the 4-wire secondary allows for easier implementation of residual current monitoring. This involves measuring the current flowing in each of the 3 phases and the neutral conductor. In a perfectly balanced system, the sum of the currents in the 3 phases should be equal to the current in the neutral conductor. However, in reality, there will always be some degree of imbalance due to variations in load and impedance. By monitoring the residual current, which is the difference between the sum of the phase currents and the neutral current, it is possible to detect abnormal conditions such as ground faults, insulation failures, and leakage currents. Residual current monitoring can be used to provide early warning of potential problems, allowing for preventive maintenance to be performed before a major failure occurs. This can help to reduce downtime, improve equipment reliability, and enhance safety. Furthermore, the 4-wire secondary configuration provides greater flexibility for future expansion and modifications to the electrical system. The neutral conductor can be used to supply single-phase loads, such as lighting or control circuits, without requiring a separate transformer. This can simplify the design and installation of new equipment and reduce the overall cost of the electrical system. Additionally, the neutral conductor can be used to provide a reference point for voltage regulation, which can help to improve the stability and performance of the electrical system. When selecting a transformer for a 480 volts 3-phase motor application, it's important to consider the specific requirements of the system and to choose a transformer with the appropriate kVA rating, impedance, and other characteristics. The transformer should also be designed and constructed to meet all applicable codes and standards and to withstand the environmental conditions in which it will be installed. Regular maintenance and testing are essential for ensuring the continued safe and reliable operation of the transformer. This includes visual inspections, insulation resistance tests, turns ratio tests, and other tests as recommended by the manufacturer. Any problems that are identified should be promptly addressed to prevent them from escalating into more serious issues. In conclusion, the 480 volts 3-phase transformer with a 3-wire primary and a 4-wire secondary is a versatile and reliable solution for powering motors in industrial applications. The neutral conductor in the 4-wire secondary provides a number of important benefits, including ground fault protection, voltage stabilization, harmonic mitigation, surge protection, simplified testing and troubleshooting, residual current monitoring, and greater flexibility for future expansion. By carefully considering these benefits and following proper design, installation, and maintenance practices, it is possible to ensure the safe and efficient operation of the electrical system for many years to come.